Today we're going to talk about three famous paradoxes. The first one will be the Monty Hall paradox. The second one will be the St. Petersburg paradox. And the third will be the gambler's ruin paradox. You're on a game show. There's three doors. Behind one door, a brand new car. Behind the other two doors, a goat. You get to pick one door. The host isn't going to open your door, but opens another door that has a goat. Here's the big question. Should you switch your initial guess? This is called the Monty Hall paradox, named after a guy named Monty Hall who was the host of the show Let's Make a Deal. Okay, let's be a little more precise about exactly what the rules are. Rule number one is that the host must open a door different than the one you've picked, and rule number two is the host must open a goat door. So the question, do you switch your guess? A fact that's surprising and has confused a lot of people is that you actually should change your guess. And if you do switch, you'll get the car with probability 2/3. Let's work that out. The way this works, and it's a bit paradoxical, is because the host is constrained to show you a goat. So what happens is that if you happen to pick a goat, the host has to show you the other goat, which allows you to switch to the car. Of course, if you happen to pick the car in the first place, then you will lose. But the chance of picking the car in the first place is only 1/3, therefore the chance of losing is only 1/3, therefore the chance of winning is 2/3. Okay, this one's known as the St. Petersburg paradox. Let's go back to the game we've talked about quite a bit, where we flip coins until we get the first head. If it turns out that it takes n flips to get the first head, in this game, you will win 2 to the n dollars. So here's a question. Would you pay $10,000 to play this game? Would you pay $20 to play this game? Let's compute the expected payoff of this game. If we let f be the random variable that represents the number of flips and let x be the total payoff, well, we know that the expected value of x, using the law of total expectation, is the sum of the conditional expectations, the expected value of x given that f equals n, times the probability that f equals n. Well, notice that when f equals n, the payoff is 2 to the n, the probability of that happening is 2 to the minus n. Those are chosen to cancel exactly, and so we get a product of 1. Therefore, we have the infinite sum 1 plus 1 plus 1 plus 1, and so forth and so on. That sum is infinite. Therefore, this game has an infinite expected payoff. That means it's larger than any other finite number. So whatever cost you would pay, the expected value of the payoff is higher than that. Does it still make sense to pay a lot of money to play this game? Okay, now in this game, what's happening is there's a large chance for a small payoff and a small chance for a very large payoff. So whatever you pay, the expectation is higher, but there's a pretty good chance you'll lose money and a small chance that you'll win a lot of money. Most people aren't comfortable with that, even though the expected value says you should. In fact, they've done experiments and asked a lot of people in surveys, and they found out that people won't really be willing to pay more than $20 to play this game. And at some level that makes sense. You don't want to risk losing some money with large probability to have a small chance of winning a large amount of money. But on the other hand, people pay the lottery. Does the lottery make sense? Or flip this around, this is like the inverse of insurance. You lose a little money on average to make sure you don't lose a lot of money through some catastrophe. So if you wouldn't play this game, would you buy insurance? Okay, now finally let's talk about the third paradox of today, called the gambler's ruin paradox. Let's let Alice and Bob be two gamblers. They're going to flip a coin repeatedly. Every time the coin comes up heads, Alice wins $1 from Bob. If it comes up tails, Bob wins $1 from Alice. Let's assume the coin is fair, so it's 50-50 heads tails. We can even assume that the coin flips are independent. We can represent x sub n as Alice is winning after n rounds of this game, and minus xn is going to be Bob's winnings. Of course, it's a zero-sum game, so whatever Alice wins, Bob loses, and vice versa. Now let's assume that Alice starts with x dollars, Bob starts with y dollars, and we play until someone runs out of money. Who's going to win it all? So a little bit more formula here. At any given stage, x sub n plus 1 is either xn plus 1 or xn minus 1, each with probability 1/2. That represents the randomness from the coin flip. If it's ever true that xn equals y, then Alice has won all of Bob's money and the game ends. If xn equals minus x, then Bob has won all of Alice's money, and the game ends. Here's the question. What's the probability that Alice wins it all? So let's define this auxiliary variable, y sub n. So it's ever true that y sub n equals y, or yn equals minus x, we define yn plus 1 to be equal to yn. Specifically, if we ever hit one of these two boundaries, y sub n never changes. However, if yn is strictly between minus x and y, we update it like we did x. It goes up by 1 with probability half, or it goes down by 1 with probability half. Now, note that the expected value of yn plus 1 is equal to the expected value of yn. To see this, note that in any one of these cases, the expectation does not change. If the process has been frozen at a boundary, it never moves, so its expectation can't change. If it's in the middle, it goes up by 1 with probability half, it goes down by 1 with probability half, so on average, it can't change either. That means step to step, the expectation of this process does not change. But then by induction, that tells us that the expectation of this y sub n is the same as the expectation as y sub 0, the starting winnings, and that's 0. So this process always has 0 expectation. All right, now let's define 3 probabilities, an, bn, and cn. So an is the probability that Alice has won everything after round n, or perhaps earlier. Bn is the probability that Bob has won everything by round n, and C of n is the probability there's no winner yet at time n. First, we're going to compute 2 relations between A, B, and C. First of all, notice that an plus bn plus cn must be 1, because one of those 3 things must be true. Therefore, their sum of their probabilities must be 1. Second, let's use the law of total expectation and condition on 3 possible events. One event is that Alice is 1, which is yn equals y. The other event is that Bob is 1, which is yn equals minus x. And finally, the third event is that no one has yet won. That's the probability that yn is somewhere in between there. With a little bit of arithmetic, we see that this simplifies our equations quite a bit. Also notice that, as we proved earlier, the expected value of yn is 0. Now here's a quote-unquote magic fact we have to use. One could show, trust me for now, that the probability c of n must go to 0 as n goes to infinity, which is another way of saying that the probability that the game lasts forever is 0. It must end at some point. Okay, so since Cn goes to 0, that actually gives us 2 equations and 2 unknowns, which we can solve. More specifically, when we take the limit as n goes to infinity, we have that an plus bn goes to 1, and y times an minus x times bn goes to 0. More precisely, if I define a hat and b hat to be those limits, then I get the 2 by 2 system. A hat plus b hat is 1, ya hat minus xb hat is 0, which one can solve. It has a unique solution, and that tells me that a hat is x over x plus y, b hat is y over x plus y. Here's the paradox. The game is fair, right? We flip a coin, it's 50-50. We can win $1 or lose $1, but the eventual outcome depends upon the level of starting capital. So if 2 players enter this game with unequal amounts of money, the player with more money has a better chance of winning, even though the game is fair.